US Physics Olympiad, year 2017, F equal MA, first round. On this competition for 25 problems, it was given 75 minutes. Please subscribe for this channel to get more interesting problems. Problem 1. A motorcycle rides on the vertical walls around the perimeter of a large circular room. The friction coefficient between the motorcycle tires and the walls is μ. How does the minimum μ needed to prevent the motorcycle from slipping downwards change with the motorcycle's speed v? Problem number 2. A mass small m hangs from a massless spring connected to the roof of a box of mass big M. When the box is held stationary, the mass spring system oscillates vertically with the angular frequency omega. If the box is dropped, falls freely under gravity, how will the angular frequency change? Problem number 3. A ball of radius r and mass small m is magically put inside a thin shell of the same mass and radius 2r. The system is at rest on a horizontal frictionless surface initially. When the ball is again magically released inside the shell, it sloshes around in the shell and eventually stops at the bottom of the shell. How far does the shell move from its initial contact point with the surface? Problem number 4. Several identical cars are standing at a red light on a one-lane road, one behind the other, with a negligible and equal distance between adjacent cars. When the green light comes up, the first car takes off to the right with a constant acceleration. The driver in the second car reacts and does the same 0.2 seconds later. The third driver starts moving 0.2 seconds after the second one, and so on. All cars accelerate until they reach the speed limit of 45 km per hour, after which they move to the right at a constant speed. Consider the following patterns of cars. Just before the first car starts accelerating to the right, the car pattern will qualitatively look like the pattern in the first row. After that, the pattern will qualitatively evolve according to next rows. Problem number 5. A projectile is launched with a speed v0 off the edge of a cliff of height h at an angle theta from the horizontal. Air friction is negligible. To maximize the horizontal range of the projectile, theta should satisfy next inequalities. Problem number 6. In the model below, the 2 cross beams and the 7 supporting strings are all massless. The hanging objects are M1 equal 400 grams, M2 equal 200 grams, and M4 equal 500 grams. What is the value of M3 for the system to be in static equilibrium? Problems number 7 and 8. The following information applies to questions 7 and 8. A train originally of mass big M is traveling on a frictionless straight horizontal track with a constant speed v. Snow starts to fall vertically and sticks to the train at a rate of ρ, where ρ has units of kilograms per second. The train's engine keeps the train moving at constant speed v as the snow accumulates on the train. Problem number 7. What is the rate at which the kinetic energy of the train and the snow increases? Problem number 8. What is the minimum power required from the engine to keep the train traveling at a constant speed v? Problem number 9. Flasks A, B, and C each have a circular base with a radius of 2 centimeters. An equal volume of water is poured into each flask and non-overflow. Find the force of water F on the base of the flask from greatest to least. Problem number 10. The handle of a gallon of milk is plugged by a manufacturing defect. After removing the cap and pouring out some milk, the well of milk in the main part of the jug is lower than in the handle, as shown in a figure. Which statement is true of the gauge pressure P of the milk at the bottom of the jug? Rho is the density of the milk. Problems number 11 and 12. The following information applies to questions 11 and 12. A small hard solid sphere of mass small m and a negligible radius is connected to a thin rod of length big L and mass 2m. A second small hard solid sphere of mass big M and negligible radius is fired perpendicularly at the rod at a distance h above the sphere attached to the rod, and sticks to it. Problem number 11. At which point the second sphere should hit the thin rod in order for the rod not to rotate after the collision. Problem number 12. In order for the rod not to rotate after the collision, the second sphere should have a mass big M given by. Problem number 13. A massless rope passes over a frictionless pulley. Particles of mass big M and M big plus M small are suspended from the two different ends of the rope. If M small equals 0, the tension T in the pulley rope is big mg. If instead the value M small increases to infinity, the value of tension is next one. Problems number 14 and 15. The following information applies to questions 14 and 15. An object starting from rest can roll without slipping down an incline. Problem number 14. Which of the following four objects, each with mass m and radius r, would have the largest acceleration down the incline? Problem number 15. Which of the following four objects, each of a uniform solid sphere, released from rest, would have the largest speed after the center of mass has moved through a vertical distance h? Problem number 16. A rod moves freely between the horizontal floor and the slanted wall. When the end in contact with the floor is moving at a speed v, what is the speed of the end in the contact with the wall? Problem number 17. An object is thrown directly downward from the top of 180 meter tall building. It takes 1 second for the object to fall the last 60 meters. With what initial downward speed was the object thrown from the roof? Problem number 18. A uniform disk is being pulled by a force F through a string attached to its center of mass. Assume that the disk is rolling smoothly without slipping. At a certain instant of time, in which region of the disk, if any, is there a point moving with the zero total acceleration. Problem number 19. A pack is kicked up a ramp which makes an angle of 30 degrees with the horizontal. The graph below depicts the speed of the pack versus time. What is the coefficient of friction between the pack and the ramp? Problems number 20 to 22. The following information applies to problems 20, 21 and 22. A particle of mass small m moving at the speed v0 collides with a particle of mass big M, which is originally at rest. The fractional momentum transfer F is the absolute value of the final momentum of big M divided by the initial momentum of small m. Problem number 20. If the collision is completely inelastic, under what condition will the fractional momentum transfer between the two objects be a maximum? Problem number 21. If the collision is perfectly elastic, what is the maximum possible fractional momentum transfer, F maximum? Problem number 22. The fractional energy transfer is the absolute value of the final kinetic energy of big M divided by the initial kinetic energy of small m. If the collision is perfectly elastic, under what condition will the fractional energy transfer between the two objects be a maximum? Problem number 23. A spring has a length of 1 meter when there is no tension on it. The spring then stretched between 2 points 10 meters apart. A wave pulse travels between the two end points in the spring in a time of 1 second. The spring is now stretched between 2 points that are 20 meters apart. The new time it takes for a wave pulse to travel between the ends of the spring is closest to. Problem number 24. A ball of mass m moving at a speed v collides with a massless spring of a spring constant k mounted on a stationary box of mass big M in free space. No mechanical energy is lost in the collision. If the system does not rotate, what is the maximum compression X of the spring? Problem number 25. A planet orbits around a star S as shown in the figure. The semi-major axis of the orbit is A. The perigee, namely the shortest distance between the planet and the star, is 0.5 A. When the planet passes point P on the line through the star and perpendicular to the major axis, its speed is v1. What is the speed v2 when it passes the perigee?